Welcome back. In the last video, we have seen that the current density J is proportional to the number of carriers multiplied by the charge per carrier multiplied by the derivative velocity of these carriers. And we have seen that this current density J has units ampere per meter squared. And we mentioned that if the charge of the carrier is negative, the direction of the current would be in the negative direction of the derivative velocity. And if the charge of the carriers is positive, the current density would be at the same direction of the derivative velocity. That's what we are seeing. The product NE with SI units is coulomb per cubic meter is the carrier charge density. N is the number of a charge per cubic meter, and E is the charge of the carrier coulomb. So this is coulomb per meter cube. For positive carriers, NE is positive, thus the current density G and derivative velocity Vd have the same direction. For negative carriers, NE is negative, so J and V have opposite directions. As an example, if we have a rod with negative charges, this negative charge is moving from right to left. So the figure shows conduction electronics or conduction electrons moving leftward in a wire. So they are moving from right to left. Are the following leftward or rightward? The current. Actually, if we are talking about the current, we are talking about positive charge or the motion of positive charge. So if the negative charge is moving from right to left, it is equivalent to positive charge is moving from left to right. So in this case, the current is moving in the opposite direction to the motion of negative charge. So it is rightward. Current density. If the current is rightward, the current density is rightward, because actually the current density is the current per unit area. So it is in the same direction of the current. The electric field in the wire. Effectively, the electric field starts from the positive side to the negative side. So if the electrons are moving, they are moving towards the positive side. So in this case, the positive side will be here and the negative side will be here. It means that the electric field also would be rightward. So effectively, the electric current, the current density, and the electric field are always in the same direction. And if the carriers are positive charge, the motion of the carrier will be at the same direction of the electric current and the electric field. If the carriers are negative charge, its motion would be opposite to the electric current and opposite to the electric. Okay. As a numerical example, here we have a cross-section area of a conducting wire. The current density in a cylindrical wire of radius r equal 2 mm is uniform across the section of the wire, and its current density is J equal to multiplied by 10 to the power 5 ampere per meter square. What is the current through the outer portion of the wire between radial distance r over 2 and r? So it is required to find out the current, the total current, in the region only from r over 2 to r, in this region. As you mentioned, the current I would be J.ds, and if or the area, sorry, J.d area. So if the normal to the area in the same direction of the current density, so it would be J multiplied by the area. So the current I would be J multiplied by the area. And the area here that we are interested in is the area of the angular ring from R over 2 to R. So the area here is the area of the outer circle by R squared minus the area of the inner circle by multiplied by R over 2 squared. So this area is the area of the annular part starting from R over 2 to R. Making some algebraic manipulation, we can obtain this area as pi multiplied by 3 over 4 R squared. And we can substitute the value of R to be 2 millimeters. So R is 0.002 meter in SI units. So in this case, A dash equals 9.424 multiplied by 10 to the power minus 6 meters squared. Now we have the area. If we multiply the current density by the area, we can obtain the current in this portion. So I equals J multiplied by A dash, and we substitute A dash with this value, and J is 2 multiplied by 10 to the power 5. So 2 by 10, 2 multiplied by 10 to the power 5 multiplied by 9.424 multiplied by 10 to the power minus 6. We can obtain the current in this portion is 1.9 ampere. The question now, what will be the situation if the current density is not uniform? Suppose that instead that the current density through the cross section varies radially with radial distance as R as J equal A multiplied by R squared, where A equals 3 multiplied by 10 to the power 11 ampere per meter to the power 4, and R is in meters square, or R in meters. So what is the current through the same outer portion? So it is required to find out the current also in this annular ring from R over 2 to R. Now the problem is not simple multiplication of the current density J by the area. It is the integration of the current density J over the area. So the area here, if we have taken incremental part of this area, it would be 2 by R dr. 2 by R dr. So this is the incremental area of annular ring. And the variation of the value of R would be starting from R capital over 2 to R capital. So this effectively the integration with respect to the area. The current would be J dot d area. And as we have mentioned, J here is not constant. So we will replace J by A multiplied by R squared multiplied by the area. Now it is required to make this integration. A and 2 pi are constant, so they can be out of the integration, 2 by A. And the remaining part is R cubed. So it is 2 by A integration from R over 2 to R cubed dr. The integration of R cubed is R to the power 4 over 4. And the limit of integration is from r over 2 to r. So by doing the integration and substituting for the limits of the integration, we can obtain the current is as 2 by a over 4, so it would be by a over 2 multiplied by r cube, r to the power 4 minus r to the power 4 over 16, which is r over 2 to the power 4, this r to the power 4 over 16. And this 4 has been taken with these two. Okay. Now substituting for the value of r, if we remember, r was 2 millimeters from the previous study, from the previous slide. So we substitute r 2 millimeters. So in this case, the value of the current 15 over 32 by multiplied by a, 3 multiplied by 10 to the power 11 multiplied by r to the power 4.002 to the power 4. By getting this value can be found as 7.1 amperes. Okay. Another example. What is the drift speed? It is required to find Vd of the conduction electrons. So we are talking about electrons as charges or as carriers in copper wire with radius r 900 micrometer. So this is the radius of the copper wire. When it has uniform current 17 milliampere, so the total current is 17 milliampere. Assume that each copper atom contributes one conduction electron. So each copper atom contributes just one electron charge to the current, and that the current density is uniform across the wire cross section. First of all, it is required to find out the current density. So starting from the current and the radius of the wire, we can obtain the current density G as I over pi r squared because it is uniform. Okay. G here is the current density on the wire, which equals the number of carriers multiplied by the charge of the carrier. So Ne, number of carriers per volume, multiplied by the value of the charge multiplied by the drift velocity. So if we have G and we have N and E, we can obtain the drift velocity. Okay. So we have seen how to obtain G. But the question is how to obtain N. Here it has been mentioned clearly that each copper atom contributes one conduction electron. So it is required to find out what would be the number of the atoms. To obtain the number of atoms per unit volume, N, we can obtain it by atoms per mole and multiplied by mole per mass multiplied by mass per volume. The number of atoms per mole is Avogadro's number. So any material has a constant number of atoms for each mole, which is Avogadro's number. Avogadro's number is 6.02 multiplied by 10 to the power 23 per mole. Mole per unit mass is the inverse of mass per mole, which here is the molar mass of the copper. So what is the molar mass of the copper? Based on the molar mass of copper, we inverse it, we find moles per mass. And the final part is mass per unit volume is the density. The mass per unit volume is the density of the material. So according to this, the number per unit volume, the number of atoms per unit volume, can be obtained as Avogadro's number multiplied by 1 over the atomic mass of the material multiplied by the density of the material. Following this, we can obtain number of atoms per unit volume, Avogadro's number, multiplied by the density of the material over the mass number of the material. So in this case, the number of atoms per unit volume of copper can be obtained as 8.49 multiplied by 10 to the power 28 per meter cube. So this is the number of atoms per unit volume for the copper, and it is mentioned that each atom contributes just one electron. So the charge would be N multiplied by E. Now the current density J, I over A, would be NE multiplied by the directive velocity, which is unknown, which would be determined. So in this case, the area is pi r squared, and from the area we can obtain the directive velocity, the value of the current over the number of atoms per unit volume multiplied by the charge carrier multiplied by the area. So in this case, the total current was 17 milliamperes. The number we have obtained is 8.49 multiplied by 10 to the power 28. Electron charge is 1.6 multiplied by 10 to the power minus 19 coulomb, and the area is 2.54 multiplied by 10 to the power minus 6. By doing this, we can obtain the directive velocity of the charge here is 4.9 multiplied by 10 to the power minus 7 meter per second. This is the directive velocity in this case. According to this result, we can note that this directive velocity is very small. Means that the electron to move just 1 meter, it may require around 2 million seconds. So it is a huge time. So the question is, if the directive velocity is so small, how we can switch on the switch and the light will be lit at the same time? That's what we are taking, what we are mentioning here. You will ask, if the electron directive velocity is so slowly, why do the room lights turn on so quickly when I throw the switch? Actually, we are not talking about the first electron in the wire when it moves to the end of the wire. No. We are talking about stream of electrons. So this stream of electrons, each electron pushes the following electron. So once the first electron push the second electron push the third electron, and so on. So at the first instantaneous time of the movement of the first electron, the last electron will move. That we are saying here, confusion on this point results from not distinction between the drift speed of the electron and the speed at which charge in the electric field configuration travel along the wire. Effectively, what is moving the electrons is the electric field. So when we started the electric field at one end of the wire, what will be the electric field at the end of the wire? The electric field effectively is moving with a speed nearly the light of speed. So the electric field speed is nearly that of the light. So electrons everywhere in the wire began drifting almost at once, including into the light bulb. So effectively, all the electrons in the wire are moving instantaneously due to the electric field at each part on the wire. It is quite similar when you open the valve of a garden hose, with hose is full with water. The pressure wave travels along the hose at the speed of sound, but the speed of the water itself is very slow compared with the speed of the sound. That's why the drift velocity is very small, but effectively, when you turn on the light turns on at the same moment. Okay?